Yeah, I guess we'll start. Everyone coming. Our speaker today is Ramon Caceres.
That's pretty good.
Ramon is lead member of technical staff at AT&T Labs. His research interests are in mobile, pervasive, and ubiquitous computing, wireless networking, virtualization, and security. He has been a research staff member at IBM Research and chief scientist of a company called Indigo, which was an award-winning provider of location-based services for mobile devices. He holds a PhD from UC Berkeley, and he is an ACM distinguished scientist. And today he's going to be talking to us about trustworthy and personalized computing at public kiosks. And so I'll let you begin.
Thank you. Hi, thanks for coming. This was work that I presented at the Mobicom conference this year, a couple of months ago in June. His joint work with Scott Garriss, who was a summer intern from University. He's now with Google. And Stefan Berger, Reiner Sailer, Leendert van Doorn, and Xiaolan Zhang were IBM, colleagues of mine at IBM. Leendert is now at AMD, excuse me. So the problem that we're trying to address is the following. How can we gain trust on public computing kiosks? These are becoming extremely commonplace. When you go to the airport and you get your boarding pass, that's a computing kiosk. They often ask you to swipe your card, and most of us do it without thinking. You should think about that some more. There's also, of course, internet cafes where we go borrow the screen and the keyboard and the mouse and the computer to do often personal email and other personal computing tasks. On these computers that we really don't know much about them. They're just sitting there. We're renting them for a few minutes or an hour. So we often reveal personal data to these public computing kiosks. And the danger, of course, is that there could be malware running on these kiosks. In fact, there often is. There's a lot of cases in public internet cafes where there's a program that records keystrokes. In fact, when we started this project, it was a summer internship project, as I mentioned, and unbeknownst to this friend of Scott, my colleague Scott, he sent mail to Scott one day. He said, Scott, I'm in Barcelona traveling for the summer, and I wouldn't believe what happened to me today. I went to an internet cafe. I rented a computer, and the first thing that came up on the screen was this dialog box saying, would you like to renew the license for the keystroke logger? And being a computer science PhD student, this person knew enough to walk away. But it is a widespread problem that there's malware running on public computing kiosks. So I hope I don't have to say much to convince you that this is a real problem that we should do something about. So there are many ways to approach this problem, and here's in a few words what we did, and of course I'll get into more detail in the rest of the talk. What we've done in particular is to leverage a personal mobile device, like a mobile phone, to challenge the public computing kiosk to prove to the device that it's not running any malicious software, and more specifically that it's only running known to be good software. And to do that, we designed a trust establishment protocol between the device and the kiosk. And if this protocol fails, the device informs the user, who can then walk away before revealing any personal information to the kiosk. If the protocol succeeds, then there's an added degree of trust you can place on this kiosk, we'll claim. Of course, in security, there's no such thing as perfect security, but hopefully by the end of the talk, I'll convince you that we've significantly raised the amount of trust that you can place on a kiosk in very specific ways. So if the protocol succeeds, the person can just sit down at the kiosk and use it normally. The phone gets out of the way at that point. So the rest of the talk will cover these topics. I'm going to first give you a sense of what the user experience is like, because we want to make sure that we're not so cumbersome that nobody would ever use this extra step of establishing trust before sitting down at a kiosk. Then I'm going to give you some more detail on the heart of the work, which is this trust establishment protocol that we designed between the phone and the kiosk. And I'll wrap up with a quick description of our prototype implementation. We did get this working on commodity hardware and software, and a little bit of an evaluation that we did. By the way, if you have any questions throughout, just please interrupt. It's more fun for me. So before we get too far into this, I want to make some important definitions and state some assumptions here. It's very important to do in any kind of security work. So what we mean specifically by a trustworthy kiosk is one that is running only the intended software. If it's running any unknown software at all, it could be malicious software, it could be benign software, but if we don't know what it is, we're going to call the kiosk untrustworthy. So for this work, we're going to assume that the personal mobile device and the software running on it is trustworthy by this definition. So there's a lot of work to be done in securing mobile devices. That's a very interesting area of work. We need to do more, certainly. But for this work, we're going to assume that the personal mobile device is trustworthy. And I will argue, though, qualitatively that it is, I'll claim, easier to place trust on a personal mobile device that's with you 24 hours a day than it is to place trust on a public computing device that's sitting in a public space 24 hours a day. We're going to furthermore assume no hardware attacks. For example, I talked about keystroke logging software. You can also put a little $1, $2 USB sniffer between the keyboard and the computer and come back and collect it later. That's a hardware attack. We're not going to defend against that. It's an open problem from the point of view of this work. However, we are very much concerned with software attacks. Software attacks are very commonplace, as I already mentioned, and they can do a lot of damage. They're easier to deploy because you can deploy a software attack from anywhere in the world onto a network computer, whereas for a physical hardware attack, you have to actually have a physical access to the computer. So that by software attacks, I mean not only keystroke logging applications like the one I mentioned, but also some more insidious attacks that I'm very concerned with, including the possibility of running a rogue virtual machine monitor on a kiosk that makes the kiosk look like it's running normal software. For even very detailed, very expert users, you can still fool that user sitting in front of the kiosk into thinking that it's running a standard set of software like Linux or Windows, when in fact underneath that is a virtual machine monitor which can make a copy of any software, any data that's on the machine. And also, we also will defend against a compromised BIOS, which is a very low-level software attack in my view. So what's it like to use our solution here? Well, this is a rough time axis from left to right. The first thing that happens in our protocol is the user needs to somehow inform the device of the identity of the kiosk that it's about to be used. Now, there are various ways to do this. If you're renting a kiosk, the kiosk provider, the internet service internet cafe provider, can give you a number to type into your phone. Or the solution that we've played with is borrowing from work done previously at Carnegie Mellon, called Seeing is Believing, where you use the camera on your phone to take a picture of a barcode that could be attached to the kiosk somehow, and that barcode encodes maybe the URL of a place to go find the barcode itself can encode a hash of a public key certificate for the kiosk. There's fairly well-known cryptography techniques to do that, and it's previous work. So we're borrowing that. At this point now, the phone has the independent identity of the kiosk. Now we get into the picture. The first thing that happens is the phone will contact the kiosk and ask what kind of software environments can you provide my user with. And this is one example from our prototype implementation on a Nokia phone. In this case, the kiosk is offering two kinds of environment. One is a very personalized environment, which is of a lot of interest to me, which is, it just says my environment here to be friendly, but in fact what this means is it's going to let me run my own personal virtual machine on this kiosk. And the second choice is just a bunch of public applications, maybe just a web browser and a mail reader, things that you might need quickly on an internet cafe. So the user is going to select one of these configurations, and now the user simply waits. It waits for the phone to complete the trust establishment protocol, which I'm going to describe. And when that's over, the phone will inform the user either the protocol failed and the phone will tell the user the kiosk is not trustworthy, you should walk away, or the protocol succeeds and the kiosk informs the user accordingly. So in between, again, the user was not doing anything, it was just waiting for this protocol to finish. At this point, and the user is now free to use the kiosk as he would normally. If it's just going to be using some web browser or an email reader, they can just sit down and use it. Or again, the case that I'm really interested in, I'm going to run my own personal virtual machine on the kiosk. So the next step is to submit the virtual machine to be run on the kiosk. And so there's an extra dialog here, which is not needed in the case of the public applications, which is to let the user choose which virtual machine, if in fact the user has more than one. If they only have one virtual machine, then this step is also not necessary. But at this point, the user can just continue to work on, do the work on the kiosk for as long as he likes. And at the end, our software is going to be careful to clean up any personal data that might have been left on the kiosk. So that's what it's. The interaction is here, choosing a kiosk configuration, then you wait for the notification of trustworthy or untrustworthy, and then optionally you choose a virtual machine. But after that, it's use the kiosk as normal. I'm sorry?
You actually study the last phase?
We implemented the last phase. Yeah, if you have specific questions. We don't, in a sense, because at that point the software running on the kiosk has been pre-verified in a sense. So we trust our own software to clean up after itself. But you could think of coming back and challenging the kiosk again if you're really paranoid. But that's the reason we didn't do that, is it's our software at that point that we've already verified. So we know that it includes the cleanup software.
Do you have complete control of the kiosk?
I'm sorry?
What control of the kiosk do you have? Do you have complete control of the kiosk?
No, it depends on what the kiosk provider wants to give you. So in the case of the public applications, the kiosk provider is providing you with an operating system and a bunch of applications. You're simply, as the user, verifying the integrity of those applications and the identity and the integrity of those applications. If you want to run a virtual machine, then you can gain more control over the kiosk. But still, the virtual machine monitor was provided by the kiosk provider. So if they choose to let you run a virtual machine, which they might not, but if they do, I would argue it's a very good thing for users, then we're going to run our own virtual machine and have that much control over the kiosk. Yep. No, this is, I'm assuming a single user kiosk at the moment.
So you're verifying software, do you also verify the configuration of the software? Or
Yes, you can.
binaries of the software?
Well, in the,
Like, give you an example of what the effect with certificate installed in the web browser.
yeah, we based the identity verification, the integrity verification on the integrity measurement architecture work from IBM Research from my previous group. And there we do have the ability to check the integrity of configuration files, almost arbitrary ones. So the prototype in particular checked a bunch of things in the etc directory in Linux, but you could add other things if you wanted to. So that's possible to do. Yeah.
Do you want to explain how the trust is established?
No, I'll get into that right now. So, so before I get into our own integrity verification, the trust establishment protocol, I want to make sure I cover some background material that's important to understand how we establish trust. And what we do is we do something called integrity attestation. So I'll give you a little primer here. We base all this on a piece of hardware called a Trusted Platform Module. It's a chip, it costs about $1. It's been on every IBM ThinkPad for the last 5 or 6 years, manufactured in the last 5 or 6 years. It's increasingly being used in servers. And it's a very interesting chip, been carefully designed by a multi-institution consortium called the Trusted Computing Group. And it gives you some very simple primitives. One, on chip, it knows how to implement some cryptographic primitives like digital signatures, cryptographic hashes, a few well-defined, well-understood things. It also gives you a very small amount of secure storage. Secure meaning it's on the chip, and it will not release this information except through very narrowly defined software interface. And it's not a lot of storage, but it's enough to store things like encryption keys, signature keys, and things like that. And the main point is that it's a piece of hardware, so that it's resistant against software attacks to the extent that it's been well designed. And the software interface, again, is very narrow between the operating system and this chip. So the chip, there's certain things, certain secrets the chip will never reveal, certain things the chip will only reveal under certain conditions. So what we do is that you can use it for a bunch of stuff like locking your disk, encrypting all the data on your disk, but what we're going to use it for is as a software root of trust. So we're going to use the TPM as a hardware root of trust on which to place trust on all the layers of software that run on the system. And the way you do that is by a technique called measuring, which is a fancy name for computing a cryptographic hash of a software module like the BIOS and storing the hash inside the TPM chip. And the way you do that is as soon as you boot the system, you want to do a static root of trust. The very first thing you run should be a few lines of code that take a cryptographic hash of the BIOS, store the result in the TPM, the BIOS, then you jump and run the BIOS, and the BIOS should immediately take a cryptographic hash of the bootloader, store the result in the TPM, and so on. So you want to measure before you run. And that way, even if one of these layers has been compromised, its image, the cryptographic hash of its binary, before it got a chance to do anything bad, was loaded securely in the TPM where it can't be disturbed if you trust the hardware properties. So you build something on top of this called remote integrity attestation. And what that refers to is that a challenger in our system is going to be the phone. A remote system asks this system, running this stack, for proof of integrity of software. And so at that point, when the challenge system receives the challenge, it will request the TPM to produce all the, a digest of the hashes that have been loading on the TPM, and it's going to ask the TPM to sign that package, this package of bits, with a secret signing key that's been stamped in the TPM by the manufacturer. And so you have a separate attestation of what software is running in the system, signed by this hardware chip. So the system then returns the signed hashes to the TPM, who can then verify the signature, make sure it's a proper TPM, and then you can trust the identity of the software. So that's basically what we're doing. The phone is going to, in our case, the phone is going to verify the cryptographic hashes of all the software loaded in the kiosk are the ones that are expected. If anything unexpected appears, you declare the kiosk untrustworthy. So let me get into a little more detail on how that works. So going back to our trustworthy kiosk example, we have our phone and our kiosk. The phone approaches the kiosk, who then makes available the software configurations that the kiosk is willing to provide. I showed you two cases, a virtual machine monitor and standard applications like a web browser. And then the user tells the software configuration the user wants, the phone tells the kiosk. I put that as trivial as it is because it actually solves a really important problem, practical problem with the whole integrity attestation business, which is if you have to keep track of cryptographic hashes for every piece of software in the world, including every software update and every version of every software, it's really, in practice, an intractable problem. But in this case, we have a handle on this because the kiosk is only going to provide a few very well-defined software configurations that the owner of the kiosk is going to make available. So if it's an airline, the airline has an idea as to what software it wants its kiosk, its boarding pass kiosk to run, and so on. So this really solves a really big practical problem. We're limiting the number of configurations drastically, which drastically reduces the number of hashes you have to work out. Yeah.
Does it talk to the kiosk or to the hardware TPM?
To the kiosk.
But the kiosk can cheat.
The kiosk can cheat, but the package of hashes is going to be signed by the TPM with a signature that can only be done by the TPM.
The kiosk can get these hashes itself from the airline. So
Yes.
you can simply copy and give the telephone the right symbol.
I'll show you in a moment. The kiosk will in fact produce the software that it claims it has. But the signature, the signed digest of those hashes can only be provided by the TPM. And remember, the trick is no. If you break public key cryptography, yes, but it depends on the strength of public key cryptography. It's pretty standard crypto. If you have a question again, please ask it at the end. I'll be happy to try to convince you some more. But let me just get to that part. So now the user has selected the software configuration. And the phone, in order to verify the integrity of the kiosk, is going to have to it needs a set of expected hashes with which to compare the actual hashes that are running on the software running on the kiosk. So it can get these expected hashes from, it needs to get them from some authority. It could be a software vendor like Microsoft. It could be the airline, a bank, depending on what the kiosk is doing. Now, by force, these expected hashes have to be signed by this trusted third party. Otherwise, the user on the phone are not going to be able to trust it. So they're going to be pre-prepared because they're known to be expected hashes, and they're going to be pre-signed by this trusted third party. Because of that, again, it's an unforgeable bag of bits, and so you can get them from anywhere. You can use the internet, the wireless internet connection, go over the network and get, or most conveniently, you're already talking to this kiosk. So in our implementation, you get this package of bits, the expected hashes signed by a trusted third party. You get it directly from the kiosk. It doesn't matter where you get them from because they're signed digitally signed by a trusted third party. So now you know what hashes to expect. Now, of course, we need to get the hashes of a software that is really running. Now, this is where the TPM comes in. Now, I showed you before what's called static root of trust. That's when you start measuring hashes from the very, very beginning of the boot time. And that works. For a prototype, we use some newer technology called dynamic root of trust. And that is one where, remember, there's no TPM chip here. You run your BIOS as normal. It could be compromised, could not be, may not be. You run the bootloader as normal. Again, it hasn't been checked. But now, you do something called establishing a dynamic root of trust, which is a more recent development in the TPM world. And for that, you have to exploit a recent addition to the x86 architecture, is an instruction called SKInit in AMD processors and senter in Intel processors. They do equivalent things. And the key with dynamic root of trust is that essentially you can start your measurements anytime. When you start the boot, a little bit later like here, or 3 days later. We're going to use it right here. After the bootloader runs, we run something, a secure loader. We wrote something called a secure loader, which executes a special instruction and will basically start measurements here. What that means is, quite simply, that the BIOS and the bootloader are not measured. But that's actually an advantage because we remove them from our trusted computing base, so we don't have to keep track of those hashes as well. The BIOS in particular is a real pain to keep track of because it's essentially a different BIOS for every motherboard ever made. So you don't want to have to keep track of all the possible BIOSes out there. So this is, again, just a practical consideration, but an important one. So now, as before, we now have a dynamic root of trust on the TPM, and we can start the measuring process from the secure loader, who measures the OS, who measures the apps, or who measures the virtual machine monitor, in the case that I'm interested in. So it's very much as before. Now, I want to stress that this, to do this, this is the required boot sequence for the kiosk. As part of our protocol, you have to require this boot sequence. Now, you could have booted this in the past, or you could insist on rebooting at the time the user is sitting in front of the kiosk. It depends on which software configuration you need and so on. But this is not absolutely required at the time the user is sitting in front of the kiosk. Just whenever the thing was booted, it had to be booted using this sequence. Now that I'm sorry. Yeah.
I don't check the BIOS. How do I know that the BIOS is not snooping on me?
Right. So, very good question. So, if you leave the BIOS and the bootloader out of the trusted computing base, then you have to make very sure that you never run the BIOS again. So, Windows, for instance, likes to call the BIOS all the time. So, if you're running Windows, then this stuff doesn't work. In our prototype, we're using Zen here, and Zen doesn't call the BIOS. But you're absolutely right. If you're ever going to use the BIOS for anything, if it's going to get a chance to run for even 1 microsecond, you have to measure it. Yeah, there's no free lunch there. So, coming back, assuming that boot sequence was in fact what took place, now we come to the integrity attestation itself, which is the phone is going to challenge the kiosk to produce proof of what software it's running now and what software was loaded. So for that, the kiosk responds with 2 pieces of information, and hopefully this will make a clear answer to your question. The phone needs a copy of the cryptographic hashes of every software module that's been loaded in the kiosk. This could be quite a long list. a few hundred, a few thousand pieces of software that's been running in a system, bin ls, state, everything that's actually loaded and running. So that is provided by the kiosk from a list kept in the kernel. It is not trusted. You do not trust this. However, to make this trustworthy is you also get a digest of the measured hashes produced by the TPM and signed by the TPM. And because of the sequence of steps where you remember you have a root of trust at the bottom, and each layer of software measures the layer above before it runs the layer above. Each layer of software has been measured before it gets a chance to do any damage. And so you can trust this digest is signed by the TPM. So the now does a bunch of crypto verification here. It replays these hashes and makes sure it matches this digest. It verifies the signature, and if everything checks out, it also then compares these measured hashes against the expected hashes, which is received in the previous step. So if everything checks out, then the kiosk is declared trustworthy because it knows that all of the software running on the kiosk matches expectations. If anything is wrong, one of these hashes will not match. And that's enough to say, I'm sorry, you shouldn't trust this kiosk. It could be that some innocuous piece of software was made to run, or it could be that a malicious piece of software is running. I don't care. Either case, I say untrustworthy. And this is really the key to the work right here.
How do you get the public key of the TPM?
Right.
You cannot get it from the kiosk, as you said before.
No. That's absolutely right. There's in the whole trusted computing group world, the TPM standard, it's assumed that there's a public key infrastructure for those secret keys that the manufacturers have stamped into the TPMs. So you need a trusted third party that will verify the identity of, well, to the integrity of the TPM itself. So you do need an external.
So your telephone has to talk to this external guy.
Well, in this case, it's a little bit like your browser already, your web browsers today. They have a set of certificate authority keys that come with the software. You will have to have this software in the verification side, the public side of the secret key for the TPM, not the TPM itself, but the certificate authority for the key for the TPM has to be put in your phone somehow. You have to get it from some third party. Yes, you're absolutely right. I'm sorry? Xiaolan. And that's according to the standard also. So the reason this is a digest, by the way, is, again, this can get quite large. And the TPM is a $1 chip, so it doesn't have a lot of memory. So what you actually store in TPM is the end of a hash chain. So let's say you hash the BIOS, you put it in TPM register 1. The operation is called extend, and the extend operation on these registers takes the current value of the register, concatenates the new value that's been downloaded, and it takes the hash of that and puts that back in the register. So it's the end of a hash chain. And that's what you get from the TPM. So you have to replay these hashes in the right order in order to try and compare it against the end of the hash chain, if that makes any sense. Yeah.
Why is it not possible for the kiosk to do sort of a replay on these digests from one session to the next?
Right. So I'm leaving a bunch of detail. Like, I invite you to look at the paper. We did. I just don't want to clutter up the slides, but there's a nonce that goes here to prevent replay. That's the easy answer. So now that was the key. Now we've established that the kiosk is running only known to be good software. And if that's the case, we go ahead and use it. This is a scenario that I've been playing with and others for quite a long time that I personally think is going to be increasingly important in the future, and that is to run personal virtual machines either on public computing devices or your own devices, your own computers at home or at work. There's work done at NU and Intel Research Pittsburgh called Internet Suspend Resume. That's work that calls, and one of the motivations for this work is securing that scenario. So this I'm just going to put it here. So what you want to do is run a personal virtual machine on the kiosk. At this point now, you trust the software on the kiosk, a virtual machine in particular. You trust that it's one that's not going to be malicious, So now you feel comfortable giving the kiosk your virtual machine, which has a lot of your personal information. So what the last two steps here in the case of the machine is the phone is going to give the kiosk the right to run the virtual machine. So to do that, the last couple of steps in our protocol here is the kiosk creates a public-private key pair for this session. It sends it to the phone along with a self-signed certificate for this key. And now the phone can give away not just the URL for the encrypted virtual machine image, which is safe to give away because it's encrypted, but then it's going to encrypt the decryption key for the VM using this session key K. And now the kiosk knows how to go get the virtual machine, decrypt it, and run it. So that's the end of the story for the virtual machine case. So a bunch of details that I did not get into here. I invite you to look at the paper. I'll put the reference up at the end. But there are a lot of cryptographic details in the protocol that we tried to be very careful about. So things that we did was we bound the attestation to the kiosk in front of the user. There is another attack, which I call the kiosk in the middle attack, which is not quite the replay attack. It's real time. There's two kiosks involved. There's a bad kiosk in front of the user, and then there's a kiosk with good software running somewhere else. And the kiosk in front of the user simply relays the attestation request to the other one. That one produces a timely attestation, sends it back, and the user is fooled into thinking that the kiosk in front of him is safe. So to do that, that's why we have to take a barcode, because we need to have the identity of the particular kiosk in front of the user. We need to know, in a sense, what's the public key of the TPM in that kiosk, and we do that by external means. You have to have another channel with which to get some way to certify the public key of the TPM for that particular kiosk. So we did that. We do the nonce, which is not on this list, to prevent replay attacks. We set up a secure channel, like I showed you that. That was the kiosk generates its own public-private key pair and a certificate. Our software is careful to clean up and wait. Again, the reason we can trust it's been done is because at this point we know it's our software. But you can certainly read the kiosk and then ask it to tell you what's there and so on. And finally, something I haven't mentioned at all is there's another party involved here, which is the owner of the kiosk. And it is concerned with liability. If an internet cafe computer is used to launch a denial of service attack against someone else, most legitimate internet cafe users don't want that to happen. So a subset of our protocol allows the kiosk owner, using a separate computer that the owner owns, to challenge the kiosk as well, and at least obtain an attestation for the layers of software that the owner is providing, up to the virtual machine monitor layer or up to the OS layer in the other case. So that's part of the protocol, and you can see that in the paper. Yeah.
Purely practical question. You said that once we do the attestation, we have faith in the nature of the software. That depends on who created the software. Mm-hmm. So if it is an airline, I can have trust. But right. If it is the owner of some cafe,
right.
So what's going on here? Who owns those kiosks? Who created the software?
Yeah, this is a very good question. So, like in the airline or a bank, the user has a pre-established trust relationship with that entity, and you trust your bank already. You trust your airline already. In the case of an internet cafe, I think the more likely authority for what good software is and bad software is somebody like Microsoft, a software vendor, not the cafe owner. So already, software companies are signing drivers. They're signing hashes of software they know to be good. Red Hat, when you get a Red Hat distribution, you can go on the side and get that. So that's the kind of information that we need. So I don't propose that you trust random internet cafe owner. Absolutely not. But if you want Red Hat 7, you should be able to go to Red Hat and ask what is a legitimate distribution of Red Hat 7 or whatever it is.
So you expect the internet cafe to provide a specific loan company which produces this software?
Right. Yeah. It'd be a standard release of or a list of standard software, which is what's behind my very friendly public apps, that's 2 words. That's so it can fit on the screen. But behind that, those 2 words, is actually a list of software versions that you have to go find the expected hashes for. So it's just for the user. You don't want to bother the user with the version number of Windows and and Firefox and Thunderbird or whatever else you want to use. But at some point, yes, there has to be an agreement on what version is expected so you can go get the right hashes. Absolutely right. So the rest of the talk, I'm going to give you an overview of the implementation and then a little bit of the evaluation that we did. So on the mobile device, we used a Nokia phone running the Symbian X60 platform and speaking to the kiosk over Bluetooth. Very standard stuff. On the phone, we wrote a bunch of software. It's one big Java micro edition application, which does what you might expect from what you've heard me describe. Certainly interacts with the user and shows this very simple interface. What configuration do you want? And later, go ahead and use this kiosk, or no, walk away. It talks to the kiosk via Bluetooth, and the most of what it does is it does all that crypto necessary to verify the attestation. It has to replay those hashes in the right order, and then check the signature and all that stuff. So it does a bunch of crypto. That's all done on the phone. On the kiosk, we use a generic PC, except that it had a fairly recent processor, so that it had the dynamic root of trust instruction in it. So we ran Zen on the kiosk with various Linux guest operating systems. This was very important. We had to have a recent AMD processor. It could have been an Intel processor as well. This is secure virtual machine technology. Intel calls it trusted execution technology, I believe. So that has the right instruction for dynamic root of trust. We had a TPM 1.2 chip in the system, of course, and Bluetooth. And here we wrote a set of software. One is a front-end application that talks to the device, accepts the attestations and so on, and presents the configurations available. There's a separate subsystem, which is previously done at IBM, called the Integrity Measurement Architecture, which has a daemon and some kernel modules that keep track of all the hashes of all the applications being run, and also stores the right things in the TPM at the right times. And we also needed, if you caught that, we needed a secure loader to execute the dynamic root instruction. So we modified reading email, things like that. So we did a web survey. We gathered volunteers from the Carnegie Mellon University population. We got 88 respondents to the survey, and it was a very simple survey. We basically, after explaining the setup, what we were trying to do, what kind of extra assurances they might expect if they run our protocol, how long would you be willing to wait before you start surfing the web in general, before you read your personal email, and before you make a banking transaction, assuming you're willing to do any of these things. And so for this, the general web surfing, particularly sensitive a lot of the time, as you might expect, most people are willing to use an internet cafe computer to do this, so just a small number of the 88 were not willing to use a public computer for web surfing. And then this is how long they were, on the x-axis, how long they were willing to wait, their opinion of how long they're willing to wait. So I'm not willing to wait at all. Less than 30 seconds or less, 30 seconds to 60 seconds, or 1 minute to 2 minutes, or greater than 2 minutes. And so you can just see what people are generally willing to wait a little bit of time to get added privacy assurances. And by the way, this looks like a long time, maybe half a minute to a minute. But in fact, at Carnegie Mellon itself, there's in a sense, a public computing facility that's well used. That's where people sit in the public computers on campus. And the computer gets personalized for them, not using virtual machine technology, but older technology from Microsoft. And we measured how long that takes, and that's taking 90 seconds to 90 to 105 seconds to give people a lot, basically the ability to start using these computers on campus. And people are willing to wait. Maybe they're not happy about it, but they're willing to wait. So that's an independent verification that this number is not wishful thinking, that people are willing to wait for a service that they want, for a personalized service. So on the email case, as you might expect, email is more sensitive. So people are willing to wait, in general, longer for added assurances that their privacy is going to be preserved. So this graph is weighted a little more towards that way. And for the banking, I'm actually very gratified to see that people are sensitive about these things. You know, most people are not willing to use a public computer for banking. That's sort of a sanity check. I wouldn't. So I'm happy to see that Carnegie Mellon students are also not willing to do that. But the ones that are, again, some of them are willing to wait quite a long time. So that's just user expectations. Now, getting to actual performance numbers of our prototype. Here's the delay in seconds in this column here for executing various aspects of our protocol. So if you have to reboot the kiosk while you're standing in front of it, which again is not required. That's only if you have a radically different software configuration that you need, or you're really paranoid, like Wade, and you want to reboot and make sure everything is. I'm just kidding. Then you're going to incur these three rows, which is not required by the protocol. Sometimes you have to do it. At some point, you have to boot the system using a particular order. If you have to wait for it in real time, then shutting down unoptimized for this purpose, Zen Linux takes about 25 seconds. The regular grub loader plus the also secure loader takes about 2 seconds. And then a full Zen plus Linux boot, not optimized for the kiosk case at all. This is a Fedora 7, full of servers that you don't need. That takes a whole minute. So that's a long time. Now, when we get into the picture, the two main parts of our protocol are you have to transfer the expected hashes to the phone. It's the hashes that are all of the possible hashes you might expect for this kiosk. So in our case here, what we evaluated was the full Zen plus Linux distribution. So it's a lot of pieces of software you may never need, but in case they run, you need to know the expected hash. So that's a big chunk of hashes. So that took 42 seconds over Bluetooth 1.2. Now with Bluetooth 2.0 or other higher speeds, local area wireless networks, this is going to go way down. And the integrity verification step, again, is the measured hashes plus the digest plus all the crypto to verify that on the phone. That took about 23 seconds. So here we're in the 60-second range, which I'll claim is close to user expectations, and there are many, many opportunities for speed up here. This was a completely unoptimized Zen plus Linux distribution, and our software is an early prototype, so there are ways to cut down on that. Another aspect of the performance is how much data are we transferring over the Bluetooth link. So the biggest thing, again, are the expected hashes. We had about almost 21,000 pieces of software that we had to hash in the Zen plus Linux distribution. The average entry, this is mostly ASCII in the prototype, is about 1.3 megabytes. That has to come over the Bluetooth interface, and then the measured hashes, in this case, Zen plus DOM0, it's about 676 pieces of software out of these 21,000 were actually executed before you walk up to the machine. And that's about 39 kilobytes. And finally, the signed digest is a standard size of a signed digest from the Trusted Computing Group is about 800 bytes. So 2 points here. All of these numbers are well storage capacities of today's mobile phones. That Nokia N90 without any extra memory cards added has many megabytes of capacity, so this is not a problem. And there's really a lot of room for compression. This is mostly ASCII, and that's mostly ASCII. So we can easily get 30 to 40% compression by just running lemplzip or something like that.
Just clearly measured hashes on the phone, right? I'm trying to understand why you transferred all the possible expected hashes to the phone.
Yeah, I guess you could optimize the protocol so that you go get the expected hashes for only the ones that you need. We didn't do that. In the way we had coded up the
Substandard plain kiosk configuration with web browser and email, or just web browser,
right.
would be a fairly limited number of hashes.
I agree. Yeah, if you sort of tailor this kiosk for one purpose, then you don't need all these. Absolutely. Okay, so that's pretty much it. I'll wrap up in this last couple of slides. I just want to point out a couple of alternative approaches to the same problem. This is a very common problem. A lot of people have thought about this. So one avenue of work that's been explored recently is to carry some trusted software on your mobile device, load that software and run it on the kiosk, and have it sort of look around and check the kiosk for you. This is, in more technical terms, you're going to establish a software root of trust on the kiosk via software that you carry on your trusted mobile device. So there's work done at Carnegie Mellon, Professor Satya and some students, and also work done at IBM with, this was a Rutgers student. I forget his first name now, but yeah, Ravi. So he did this summer internship at IBM with some colleagues of mine. So this is a viable approach. I'll claim, though, that by basing our work on a hardware root of trust, we're able to protect against more attacks. So, for instance, they're vulnerable to a virtual machine monitor that's running in the system. That makes it look like they're presenting a raw machine to their software, but in fact it's a virtual machine. So with the hardware root of trust, we can defend against that, as I hopefully convinced you. So that's the advantage, of course, for them is that they don't require the TPM check. Well, we do. So plus and minus. A different approach is one that's been followed by a number of people. This is Roy Want at Intel Research. This guy is at Citrix now. And this was Xerox at Park. And the idea here is to leave the phone sort of in the loop even as you use the kiosk. And anytime you're going to either enter or read sensitive information, you don't put that information through the untrusted kiosk, but you funnel it sideways through the phone. So you have the phone sitting next to the kiosk, and depending on what you're doing, sometimes you interact with the kiosk and sometimes you interact with your phone. And this has the advantage, it doesn't need a TPM, and you really never trust the kiosk. So the kiosk never gets to see any sensitive software at all. On the other hand, it has the disadvantage that you're forced to interact with this very limited mobile device. And you're also forced to, say, if you're running a website, you're forced to program the website differently so that it knows to split the sensitive information and send it to the phone and send the insensitive information to the kiosk. So it takes extra software work, but it has its advantages and disadvantages. So you should think about that as well. So that's definitely an alternative. Anything else? Okay, so that's really all I had to say. What I presented today is a way for leveraging a trusted personal mobile device to establish trust on a untrusted public computing device before giving any personal information to that public computing device. I'll claim this is a very commonplace situation, and most people are blindly placing trust on these public computing devices, and we should work hard to improve that situation. So I hope I've convinced you that at least we've raised the bar by establishing a protocol between the personal mobile device and the kiosk that determines the identity and integrity of the software. We have not improved the hardware attack problem, but I claim we have made an improvement in how much you can trust the software on the kiosk by doing this protocol. We have built this on commodity hardware and shown that it works and performs reasonably for at least for an unoptimized prototype. And furthermore, again, we have focused on this use case that I'm very interested in, which is fully personalizing the kiosk by running my own personal virtual machine on it, which gives me the ability to run my own applications, operating system, my data, all my settings. My cursor will be right where I left it the last time I used the virtual machine. It's just like carrying a laptop without carrying the laptop. And I hope that if you think this through, you'll see that this trust establishment protocol is applicable to not just the kiosk case, but any number of these situations where we want to establish trust on public or pervasive computing infrastructure. There's lots of cases. There's a bank ATM. We're talking about using displays, pervasive displays. All these cases, I think, will become more and more common as computing becomes more ubiquitous and we use more public computing facilities and not carry them with us all the time like we do these laptops. So for more detail, I refer you to the Mobisys paper. Thank you for your attention.